Well, good afternoon, everyone. My name is Chet. I'm the Director of Technical Service for Toray Composite Materials America. And I'd like to take a few moments today to talk to you about materials that Toray Group is currently providing into the hydrogen market. And in particular, I'd like to focus on carbon fiber for transportation and storage of hydrogen through composite overwrapped pressure vessels. Well, who is Toray? Well, Toray was founded in 1926 mainly as a fibers and textile company. As you can see, our tagline is innovation of chemistry or biochemistry. And over the years, we've certainly lived by that credo and moved from textiles into performance chemicals, carbon fibers and composites, environmental engineering, and life sciences. We currently have 317 subsidiaries and affiliates, and we're approaching 50,000 employees. So we're a couple of years away from our 100th anniversary. So we've been around for a while. As a global company with almost 100 years under our belt, we realize the importance of sustainability, and Toray is dedicated to that vision. We are dedicated to providing products into the four pillars of sustainability, whether it be climate change, recycling, clean water and air, or medical care and hygiene. And some of the products you'll see there on the right side, carbon fiber, for example, currently going into aircraft to reduce weight, reduce the carbon footprint, a number of membranes for recycling, and reverse osmosis membranes for clean water, along with protective clothing and antibody drugs for the medical care. So in the United States, Toray has a number of facilities. The ones noted by the dark blue boxes are ones that are currently providing materials into the hydrogen market. The carbon fiber that I will talk about is being produced in Decatur, Alabama, and Spartanburg, South Carolina. Well, what is carbon fiber? Well, it's basically crystalline filaments anywhere from 5 to 7 microns, comprised mainly of carbon fibers, oriented chains, long chains. They have unique characteristics like high stiffness, high tensile strength, high strength to weight ratio, good chemical resistance, good thermal tolerance, and low thermal expansion. So these properties lead into unique applications in aerospace, civil engineering, military and defense applications, industrial, automotive, sports, and recreation. On the bottom there, you can see some of the applications. Obviously, aerospace is big for us. The Boeing 787 primary structures. The second picture, you'll see of an overwrapped pressure vessel. Also, in the military and defense, we have filament wound motor casings for rockets and missiles. Sports and recreation, high modulus fibers. For example, going into fishing rods, hockey sticks, golf clubs, etc. One of our other industrial uses is for tension members for power transmission lines, and then automotive as well. Well, how do you make carbon fiber? 95% of the carbon fiber that's produced is pan-based, polyacrylonitrile. So we start out with acrylonitrile. We go through a polymerization process. In solvent, we concentrate that down into a dope. We then pump that through spinnerets in a coagulation bath to generate individual filaments. Then it goes through a series of drying and drawing. And then you wind up with polyacrylonitrile. We call it white fiber. So that's the pan precursor for carbon fiber. And these fibers, each end, or toe end we call it, can have anywhere from 12,000 to 24,000 individual filaments, and those filaments anywhere from 5 to 7 microns. So once you make the pan, the next process to convert it to carbon fiber is a series of thermal treatments. The first one is what we call oxidation, anywhere from 200 to 300 degrees C in air. And if you look at the bottom process flow there, basically what you're doing is you're closing up the structure and you're removing non-carbon atoms. So the second step is actually a pyrolytic process. Carbonization at anywhere between 1,000 and 2,000 degrees with a heavy nitrogen blanket. If you want high modulus fibers, there's another step called graphitization. It's not necessary to do that unless you're looking for high modulus fibers. Sorry, those numbers are wrong there, but it's anywhere between 2,000 and 3,000 degrees C, again with a heavy nitrogen blanket. The final step is surface treatment and sizing application before it's spooled up on the rolls and sent to the customer. So how's carbon fiber an enabling technology for the hydrogen industry? Through carbon overwrapped pressure vessels, composite overwrapped pressure vessels for transportation and storage of hydrogen. If you look at the pressure vessel types on the left, type 1 is fully metal, usually steel. Type 2 is steel or aluminum with a glass hoop layer of composite. Type 3 is a metal liner, usually aluminum, with a composite overwrap. And then type 4 is all composite. The lining itself is a plastic liner, usually high density polyethylene, with a carbon fiber or carbon fiber glass hybrid overwrap. So what are the advantages? The advantages obviously in moving from type 1 down to type 4 is reduction of weight. So you're reducing weight per unit volume stored. The disadvantages, cost. Cost of composite materials increases the manufacturing cost of these liner types, but it's a balancing act. So, is it worth the advantages to go into the increased cost? So let's talk about that. So what are carbon fiber composites important? Reduce fuel system and vehicle weight. For large buses, for example, or trucks, using type 3 and type 4 COPVs can reduce fuel systems by as much as 1,000 pounds. Also, the vessels extend the practical limit of containment and provide better storage density. For example, cylinder ratings of 5,000 psi and above, type 3 and type 4 represent practical solutions to that. And also, composite materials significantly improve the corrosion resistance and the overall safety of the pressure vessel itself. So how do you make a COPV? COPVs are usually filament wound carbon fiber with epoxy resins. The picture on the far left on the top is actually, it shows the liner itself with the initial hoop layers being placed onto the liner. As you move to the right, you finished up the first hoop layer. That reinforces the body of the vessel. And then the next, you put helical layers on to reinforce the dome ends. And so the number of layers that are present in the tank depend on tank design and what the tank performance needs to be. Then you do a cure and you wind up with a final product. A couple of examples of COPVs on the bottom made with Toray fiber. Back of cab type 4 700 bar hydrogen tanks, and also a 5,500 PSA type 4 tank for aerospace applications. Each one of these is 27-inch diameter by 80-inch minimum length, so they're fairly large tanks. Well, one of the things that we need to think about as a carbon fiber manufacturer is the growth trend. We see the growth in COPVs expanding rapidly. So that brings into question, we have our base customers and we're still supplying those. Those businesses continue to grow. We see from 2020 to 2023, we saw an average growth rate of 27%. but the COPVs are expanding rapidly based on government incentives and global positioning. So how are we going to supply that demand and maintain the demand in our current customer base? If you look at the projections just for COPVs, it's steadily increasing. By 2030, for both CNG and CHT, we're looking at 110,000 metric tons carbon fiber needed. And then Toray's done their own analysis, and they see through the end of 2025 a 42% rate up to 40,000 metric tons needed for both CNG and CHG. Well, if you look at hydrogen alone, the projected volumes are 38 to 40,000 metric tons. Just to give you an idea, 38 metric tons takes 19 lines of capacity, 19 carbon fiber manufacturing lines, assuming 2,000 metric tons of T700 type fiber. So obviously, if this demand grows, there's going to have to be capacity expansion to meet the needs. And just as a point of reference, lead time for a new carbon fiber line is roughly 2.5 years. That includes, obtaining the capital, obtaining all the equipment, the construction time before production, usually 2.5 years minimum. So with the potential for all this growth, Toray and other manufacturers have announced expansions. For us, Toray, we're expanding 6,000 metric tons of capacity, 3,000 in Spartanburg, South Carolina, and 3,000 at our facility in South Korea. These are standard tow expansions, so 12 and 24K expansions. And so at the moment we have about 29,000 metric tons of standard tow capacity. After expansions, by the end of 2025, we should be at 35,000 metric tons of standard tow. And again, we have 35,000 metric tons of large tow, 50K tow. So we're a leader in advanced composites. We got state-of-the-art materials, high volume production capacities. We have public allowable database materials available, and we're fully integrated in the supply chain. So we have a broad portfolio of products serving a number of different industrial areas. Toray, we feel like we're positioned to participate in the growth from a fiber standpoint. We have a large portfolio of fibers. We have a long history in the use of filament wound COPVs, mainly for CNG. Now we see more and more of our material going into hydrogen applications. T700, Toray's T700 has been the industry standard for a number of years, but with hydrogen coming on board, people are starting to move to improved property fibers to be able to take more weight out of the vessel itself. So we're currently developing a product for the hydrogen market with targets of 6 gigapascal tensile strength and 260 gigapascal on the modulus. And then again, currently expanding our capacity. Well, Toray Group, as a group, not only produces carbon fiber for the hydrogen market, we also provide materials for a number of applications in the hydrogen chain, from production all the way to use. If you look at the blue boxes, so some of the things that we offer to the industry are water treatment membranes to provide clean water for the electrolyzers, obviously carbon fiber for the wind blades for renewable clean electricity. Internals of the electrolyzer, we also provide materials such as diaphragms, carbon paper, gas diffusion layers, CCM, and other parts. Again, on the transport and storage, carbon fiber, the liners, and also the membranes and resin parts that we mentioned earlier. Same thing for the use for hydrogen consumers. So that's sort of Toray in a nutshell and some of the materials that we're providing. We ask you please come by and see us at booth C34, just adjacent to the stage here. Myself and Tim Kirk could answer questions that you might have about carbon fiber, and we have a number of colleagues from the Toray group that can answer questions about the other materials that we discussed, like membranes, et cetera. Thank you very much.